In this presentation, I'll be introducing VegyRap, a specialized QGIS tool designed for the optimal hydraulic design of flexible line channels. Natural water channels are often susceptible to significant risks, most notably scour and erosion. To mitigate these issues, lining the channel is a common solution. There are two primary categories of channel lining, rigid and flexible. Rigid linings typically involve materials like concrete. Flexible linings, which are the focus of today's talk, can consist of vegetation or riprap. VegyRap is an open-source GIS tool that integrates seamlessly with the QGIS platform. It's specifically developed for designing open channels with flexible lining, whether that's vegetation-lined or riprap-lined. The tool is structured around 2 plugins and 3 core modules. Let's take a closer look at the workflow. The first component is the VegyRap plugin. This allows users to digitize the channel's path directly on the canvas. It also facilitates the download of relevant digital elevation models, DEMs, along the channel corridor. Using these inputs, the optimizer can then determine the ideal longitudinal profile for the channel, effectively minimizing earthwork volumes and overall costs. The second component is the VegyRap plugin. This plugin is used to optimize the channel's cross-section, aiming for the most cost-effective design for either vegetation or riprap lining. Once the least cost section is established, the tool can perform a reliability analysis to monitor 4 key risk indicators. Users can also conduct a sensitivity analysis to identify which design parameters have the greatest impact on the relationship between cost and risk. Finally, the tool supports dual optimization analysis using Pareto fronts, helping users find a compromised solution that balances reduced risk with a manageable increase in cost. Now, let's transition to QGIS to see how VegyRap works in practice. Starting with QGIS Open, we've already added a base map from OpenStreetMap and zoomed into the specific area we're going to be working on for this project. Now, let's navigate to the Plugins menu and select the VegyRap plugin to launch it. With the VegyRap dialog now open, the first step for preparing our DEM is to define the source for our route alignment. We have 2 options here. We can either import an existing line or draw it directly on the map canvas. For this exercise, I'm going to choose Draw it on Canvas. Next, we need to specify the source for the digital elevation model. VegyRap offers 3 different sources for the DEM: SRTM at 30-meter resolution, ALLOS at 30 meters, or a higher resolution 12.5-meter option. I'll go with the SRTM 30-meter data. We also need to set the buffer width around our route. The default is 2 kilometers, but you can adjust this up or down based on your specific project requirements. This next step is crucial. We must correctly set the UTM zone for our project location. My project area is in Saudi Arabia, which falls within UTM zone 37, and since it's above the equator, we select the Northern Hemisphere option. To actually download the DEM data, we need to provide an API key for OpenTopography. I'll paste my key into the designated field here. With that said, we are ready to begin tracing the path of our channel. This is the stream I intend to design. I'll now demonstrate how to trace and define the route in the plan view. Following the course like this, I'll continue tracing until I reach the confluence point, which will be right here. To finish drawing the line, simply right-click with your mouse. The route is now complete. You'll see a confirmation message saying, digitizing route added as VegyRap. And if we look in the Layers panel, we'll find a new layer called Transroute has been created. We'll click OK to proceed. Next, I'll click the button that says Download Process DEM. Now, we just need to wait a short while for the DEM data to be downloaded. Remember, you need an active internet connection for this step to work. Great, the DEM has been successfully loaded for the 2-kilometer buffer zone we specified. Let's take a look. If I zoom out a bit, you can clearly see the buffer area, this 2-kilometer wide corridor along our traced route, so our DEM is now ready. The next step is to generate a profile along our route. We'll go to the Route Profile tab within the VegyRap plugin and select the Generate Elevation Profile option. This tool will create an elevation profile based on the DEM we just downloaded. As you can see here, the profile has been generated. This is the longitudinal profile of our trace stream channel. Now that we have the profile, one of the first things we can do is initialize the channel bed. This process helps calculate an average slope for the entire channel, and now we have the average slope value. Here is the calculated average bed slope. You can see the information displayed. The slope here is approximately 0.5%. The tool also provides initial estimates for cut volume, fill volume, and the net volume for this average slope alignment. The initial average slope provides a starting point, but we can often achieve a more efficient design. To improve upon this, we'll use the Optimize Channel Bed Profile function. I'll click on the Optimize Channel Bed button, which will automatically switch us over to the third tab. In this optimization tab, we need to define some parameters. First, we specify the minimum length for each individual reach segment within the channel. The default is 400 meters, and I'll keep that for now. Below that, we set the constraints for the minimum and maximum allowable bed slope for each reach. I'll also leave the minimum and maximum slope constraints at their default values for this run. Then, all we need to do is click Run Optimization. This calculation will take a few moments. Okay, the optimization has finished, and results are now available. To visualize the optimized profile, I'll go to the Profile Plot section. Here we can see the optimized channel bed profile in orange. The summary tells us that using 23 reaches, each approximately 400 meters long, the calculated total earthwork volume is about 22,000 cubic meters per meter width of the channel. We can also see the difference between the cut and fill volumes is around 2,900 cubic meters. And the slopes across the reaches now range from a minimum of 0.1% to a maximum of about 1.37%. If I'm satisfied with these initial results, I can also explore the relationship between the number of reaches and the earthwork volume. As this chart illustrates, there's a general trend. As the number of reaches increases, the total estimated earthwork volume tends to decrease, which is typical. The red line on the chart tracks the balance between the cut volume and the fill volume. Ideally, in channel design, we aim for the lowest possible total earthwork volume while also achieving a good balance between cut and fill, meaning the difference between them, represented by the red line, is as close to zero as possible. This helps minimize construction costs. Now that we have this optimized set of slopes, we can use them as a basis for designing our channel in the subsequent steps. The next step is to open the plugin menu and activate the VegyRap plugin. To begin, we'll enter the design flow as 40. For simplicity, we'll assume the channel consists of a single reach and use the average slope. We'll set the channel pattern to straight, though any sinuosity could be used. Next, we'll choose a flexible lining and specifically select the riprap lining option. We'll then enter the unit costs for riprap and earthwork, accepting the default values provided. For the design constraints, I'll set the maximum bed width limit to 100. I'll also keep the default ranges for the maximum critical and minimum supercritical Froude numbers, and then initiate the channel design process. I'll wait for the design calculation to complete. The solution is now displayed. The optimal value is shown, with the feasible range indicated in green and the infeasible range in pink. The point representing the minimum cost is also visible. More details about the optimal solution can be accessed here. This includes the Manning's N, mean velocity, and Froude number. Additionally, we can see the flow type, the adopted side slope, and the optimal D50 value. The results also show a bed width of 7 meters, along with the bed shear stress, side shear stress, water depth, and other parameters. A cross-section view is available, providing further geometric information. In this view, we can adjust the plot size and clearly see the bed width and the overall channel geometry. With the least cost channel dimensions found, we may want to assess the reliability of this cross-section. We'll click the Reliability Data Entry button to begin inputting the necessary information. For the reliability analysis methodology, we'll use Monte Carlo simulation with 20,000 iterations. We need to define the uncertain variables. For discharge, we'll assume it follows a log-Pearson type 3 distribution. We'll set the coefficient of variance to 0.5 and the skewness to 0.1. For the bed slope, we'll account for its natural randomness by using a uniform distribution with a 10% variance. The Manning's N will be treated as a normally distributed variable. For this, we'll adopt the default variance of 0.1. This completes the setup of uncertain variables for the reliability analysis. Next, we'll move on to selecting the failure modes and assigning their weights. We will include the overtopping mode of failure. We'll also incorporate the other 3 failure modes: erosion, siltation, and oscillation. For each failure mode, we'll assign different weights based on their perceived importance. Overtopping is given the highest weight of 0.75. Erosion and siltation are each assigned a 10% weight, while oscillation is given a 5% weight. These weights reflect the relative importance of each mode in contributing to an integrated failure. After setting the weights, we'll run the reliability analysis by clicking the corresponding button. Once the analysis finishes successfully, we'll confirm by clicking OK. The reliability results are now presented. This includes the distribution of the adopted discharge and the Manning's N values used in the simulation. We also see the sampled water depths from the 20,000 iterations, along with the corresponding shear stress values. Similarly, samples for velocity and Froude number are displayed. The integrated result shows the failure ratios for the different modes. For instance, the overall failure probability, combining all modes, is about 39%. The weighted failure probability, incorporating the assigned weights, is approximately 5%. Examining the 4 individual failure modes, the highest probability, around 38%, is associated with scouring. The other modes have much smaller failure probabilities. Consequently, the overall failure is dominated by scouring, leading to the 39% figure, while the weighted failure is only about 5%. The graph confirms the adequacy of the 20,000 iterations. The overall failure ratio stabilizes as the number of iterations increases. As noted, this stable value is around 39%. The next step is to perform a sensitivity analysis. We'll switch to the sensitivity analysis module and select the parameters we wish to investigate. I'll choose the channel bed width, water depth, channel slope, and D50 for the sensitivity analysis. Then run it. This analysis helps identify which parameters most strongly influence the cost-risk relationship. We'll wait for the sensitivity analysis to complete. The sensitivity analysis is now finished, and we can review the results. Let's go to the results section. Each panel displays a variable on the x-axis against the corresponding risk on the y-axis. For example, the panels show bed width versus risk and total cost, water depth versus risk, and so on. Similarly, there are panels for channel side slope and for D50. Examining all these parameters, the most significant one affecting the overall risk index in this case is D50. The graph clearly shows that as D50 increases, the overall risk index decreases substantially. This is logical, as the dominant risk we identified was from scour. We now have two options. We can manually edit the section dimensions. The least cost solution gave a bed width of 7 meters, a water depth of 2.6 meters, and a side slope of 2.5. The optimal D50 was 130 millimeters. One approach is to manually adjust these values, perform a new hydraulic analysis, and then rerun the reliability analysis. Alternatively, we can conduct a Pareto optimization. Clicking the Pareto optimization button opens a new window. Here, we can search for a design that minimizes risk, subject to a maximum allowable increase in cost. The default cost increase limit is 5% above the least cost solution. The goal is to find the minimum risk index achievable within this 5% cost increase. We'll also select the parameter to monitor, which by default is the overall risk of failure. We'll keep that as is. The alpha value is important for resolution. A value of 0.5 provides a coarse resolution. To get a finer resolution, we decrease this number. However, a smaller alpha increases computation time and demands more processing power. The default is 0.5, but I'll reduce it to 0.1, keeping other settings as default. We'll start the dual optimization and wait for it to complete. Waiting for the run to finish. The run is now complete. We can close the window and proceed to print the Pareto results. We have the option to print or export the data as a comma-delimited CSV file. Let's export it and then open it in Excel. The data can be converted to an Excel format. This is what we have now. The exported data includes all the runs, showing the cost, the corresponding risk. We can now plot the Pareto front. Let's plot cost on the x-axis and risk on the y-axis. The resulting plot shows the Pareto front. Where increasing cost leads to a decreasing risk indicator, a smaller alpha value would yield more points and a higher resolution front. We can also review the Pareto results directly. I'll also print the Pareto results and examine the values. This view shows the optimal value and the corresponding best configuration of design parameters. The point identified here is the one with the lowest risk indicator while not exceeding the 5% cost increase limit. This is why the model selected this specific point.